So here we have a problem that has been able to reach equilibrium. That means that we can use KEQ and find equilibrium concentrations using an ICE table, which I created down here for us. And also in the first sentence, there is mention of moles and liters right here, which can actually be used to find the molarity. And I've written the formula right here. And so first off, let me create the equilibrium expression, which will work as my ultimate formula. So it should be noted that stoichiometry actually contributes as an exponent to the equilibrium concentrations. And these brackets actually indicate that equilibrium concentration. Great. Now I have this, I need to solve for a concentration using the ICE table. So initial concentrations of our reactants can be calculated from the question stem, as mentioned earlier, using molarity. So it says I have 3 moles in half a liter container. Give me 6 molarity. N2O4. And the products are not added to the reaction at the start, staying at 0. And so during the change, we cannot observe the actual rate at which reactants and products are changed, so we can express both as X. And considering how the destruction of a reactant contributes to the formation of a product, they would be minus and plus respectively. Finally, we must consider stoichiometry, as it does play a role in the concentration of the molecules making the products 2X. And the stoichiometry I'm referring to can be seen right here. And finally, moving the variables from the initial and changing concentrations, we can get values of the concentrations at equilibrium and plug this in to our equilibrium concentration or expression. 6 minus X and 2X. And we should also note that our question asks for the equilibrium concentration of NO2, which is here as 2X. So this is very important. We actually also have the KEQ value in the question stem, which is given to us right here. So we could finally write this. And so you might have noticed that we have this weird polynomial that looks difficult to solve. And so a common trick is to look at the exponent value of the KEQ number if it is provided. I'm talking about this number right here. And so a high KEQ exponent or number will indicate a fairly high preference for product production. However, if you see a very small number, which is the case here, then reactants are favored. And so in this case, the X variable is so small that it can be removed from the denominator. So you may see a rearrangement very similar to this. And so this makes the math much easier, and finally we can solve for that X value, which is the equilibrium concentration that we assigned prior that we do not know. And so solving for X and doing some math that I did before, get this value. And finally, we want to remember the info from our ice table and the NO2 concentration at equilibrium, which is 2x. So our final NO2 concentration equilibrium